Hi everybody, welcome back to Chem 161. Guess what it's time for? More Chapter 3. Yeah, that's how I feel about it too. We are making good progress through it though, so eventually it will be over. What do we have for agenda items? Lab worksheet number 4 is due next week on Tuesday. That's the soft deadline. It covers a lot of the stuff that we're covering in Chapter 3, so make sure that you are doing that as you go. That'll give you a better understanding. As the announcement that I sent out announced, today I'm going to give you the secret of chemistry. Like literally, the whole principle behind all of chemistry is in this lecture, which is why it's important. But first we have to talk about electron configurations for ions. That's the wrong button. There we go. We did electron configurations last week. That's where we ended. Now I need to do this with ions. And so this is going to require us to change the number of electrons that are present in the atom, either by adding or subtracting, depending on what the ion that we're doing. So the first thing that we're going to look at is anions, because anions are easy. If you add electrons, you just add them on as if you were looking at an element with more electrons. So add them to the next sublevel that you would expect. But if you are taking electrons away, you would think, oh, I just subtract the 2 electrons that are at the end of my electron configuration. And that's where we get you. So this slide is written to be matched up with the textbook. So the order for valence electrons will be P and then S. You won't see these. This won't really occur, so don't worry about that. And so the trick that we care about is we are going to remove electrons from the valence shell. Remember how on the electron configuration section I said your textbook talks about how d electrons are valence electrons for transition metals and all that stuff. And like, yeah, that's technically true, but for our purposes, we're going to just call the valence shell the highest n, and we're going to take away those electrons when we ionize. And this is where that helps us, is now we just remember, oh, it's the highest number n. I take away those electrons. Yeah, and then you're done. It's great. Now, that does mean that you start removing electrons from the middle of the electron configuration sentence, because they're still valence electrons. Remember, valence electrons are on the outside, and if I am grabbing electrons away to take them away to make the cation, I'm grabbing the electrons that are on the outside. They're the furthest from the nucleus. They're not the highest in energy, but they are the furthest from the nucleus, and so that's the ones that we grab, because those are the ones we see. So let's start by writing the electron configuration for O2-. So first, let's write it for O. So oxygen would be 1s2, 2s2, 2p, 4. And now if I want to do this to it, that would be the same as me adding an additional 2 electrons. So I'm going to add an additional 2 electrons. There you go, no problem. That's easy enough. We can do anions, no problem. But let's do this for iron with a +2 charge, and it's going to be a little bit different. So here's iron by itself, first of all. So we'll do the shortcut method here because iron has a lot of electrons. So argon, 4s2, 3d, 1, 2, 3, 4, 5, 6. So this is what we've got. Now I'm going to take away 2 electrons by making it 2+. And you might think, oh, I'll just get rid of these because they're the last ones. But no, remember, when we have a positive, we remove from the valence shell first. What are the valence electrons? That's these 2. So these are the ones that get kicked out. So the electron configuration for iron should be Ar, or argon, 3d6. And that's actually what we get. You'll notice that down here, I've written this because just to show you where those electrons went, but you would not write that term in your sentence. You would just omit it. So you would completely leave that 4s0 out because there's nothing there. Now, what if this was Fe3+? So if I made this a 3, what's the next electron you take? Well, now you take from the new valence shell. There is no more n equals 4. That's gone. So now the new valence shell would be n equals 3, and you take the highest energy electron, which would be this one. So that would be Fe with a +3 charge. So that's how we do electron configurations for ions. For anions, add the electrons in, no big deal. Just it's like you had a bigger atom instead. Removing electrons, take from the valence shell first. Okay? Remember, the valence is the highest n. So I've got some electron configurations for you to write out. Don't worry if they seem to be unstable or not. Like, these are not going to follow the octet rule that you probably recall from 140. These are just for practice. So write the electron configuration based on what you see here. Start by writing the normal neutral atoms electron configuration and then modify it based on what you see for plus or minus. Make sure you are cautious for some of these because I'm going to just put a little asterisk next to this guy. Remember the half-filled and D5 and D10 rules for that. Okay. Give you 5 minutes to do it. We'll go over the answers in just a bit. Type your answers in the chat to the best of your ability when you are done, just so I know that people are actually doing okay. All right, one more minute. We'll go over the answers. All right, let's go over these. So let's write the electron configuration for sulfur first. So regular sulfur would be, according to my periodic table, so we'd start with neon. Then we go 3s2, 3p4. But I need to add 2 extra electrons for this 2 minus here. So this 4 will become a 6. So that should be neon. Or not neon, I'm sorry. That should be sulfur with a 2 minus on it. Yeah, make sure you include your noble gases. That's important. For copper here, we would write, so copper starts at argon. And then we have 4s2, 3d9. But remember the d10 rule. So if I'm going to land on 3d9, I want to steal 1 to get to 3d10. And the reason that's important is because now that when you take this away, you get rid of this guy, and that's the electron configuration. For calcium 2+, let's do calcium. So that's argon 4s2. So that's regular calcium. Now I'm going to +2 it, which means I get rid of these two. So calcium 2+ is literally just argon in terms of its electron structure. Is there an electrons tab? I don't know if I've seen that. Let me look at that. Oh, look at that. Yeah, that is really cool. Let me capture that. That's pretty neat. Okay, so I didn't know that this was a thing. But if you kind of... I have to make it small, unfortunately, to capture all of this. But if you click on electrons up here... Oops, let me get my... There we go. Clicking on these elements... Ooh, why did it slow down like that? For example, if oh, I see why it's rendering the orbitals down here as I hover over them. So it's going to be really slow every time I hover over something. So I want iron here. Because Chrome doesn't actually use my graphics card for some stupid reason. So this is all being done by my GPU. It's going to take a second. If you click on an element, it'll show your electron configuration here. It'll show the orbitals down here at the bottom. And I guess it tells you other information about it. So you can see that. That's kind of neat. And you can see that when you click on other things like copper, like it follows the exceptions here, as you can see. So yeah, you can see all this stuff put together. That's neat. Thank you. I was not aware that that was a resource that was available, but that's super useful. Yeah, P-Table is really awesome. I recommend just like playing around with it and seeing what you can learn. But I have to change it back to properties, otherwise my computer might crash. Because it really does not like drawing pictures in my in a web browser or doing 3D models. All right, let's do nitrogen. So nitrogen is 1s2, 2s2, 2p4, 3. There we go. Now we have to plus it. So that means that this 3 becomes a 2. So let's just neaten that up here. There you go. B minus is 1s2, 2s2, 2p1 for just boron. I'm going to minus it by adding an extra 1 in there. There you go. Interesting, those have the same electron configuration. Well, yeah, they have the same number of electrons, right? So as long as I don't have any valence shell nonsense, I'm going to land on the same result. B minus should have 6 electrons. N plus should have 6 electrons. I bet carbon will be the same thing too, and it totally is. All right, so chlorine 2 minus would be neon 3s2, 3p5 for regular old chlorine. Then I got to 2 minus it. Be very careful. Don't do this. That's wrong. And the reason that's wrong is because p only holds 6 electrons. So we got to go like this and then go to the next one. So be careful. Don't just stick higher numbers in there because, again, there's a limit to how many electrons you could fit in each box. And if 3p looks like this, that next electron's got to go up here. Use hardware acceleration when available. I'm going to look into that during the break. Thank you. I'm pretty sure I've looked for that setting and just never found it. Or when I clear Chrome or something, like it resets my settings. I know it does that all the time because I frequently have to just clear all the cache out for everything because I'm constantly having to deal with like browser, what are they called? Extensions. Basically ad block shit and stuff that doesn't work, and then I have to uninstall it and reinstall it, and then everything goes to crap, so. Use an ad blocker, you guys. Don't browse the internet with ads. Like, that's ridiculous. All right, that is electron configs for ions. So now you can do this for ions and for any regular atom you want to. The next section, hey, here comes the secret to chemistry. Are you ready? I mean, we've known each other for, what, 8 weeks? I think I can trust you guys with the secret to chemistry. So before we talk about the secret to chemistry, let's look at a trend that we're going to talk about. This trend is ionic size, or atomic size. In 140, we really briefly talk about atomic size, and I just say, hey, if you go down the periodic table, atoms get bigger. If you go to the right, they get smaller for reasons, and I'm all shifty about it. You can't see me being shifty, but my eyes are going back and forth in a shifty way. In this class, we're going to explain that to a absurdly high level of detail. So here we go. So first, let's define what we mean by the size of an atom. So the first thing we're going to do is define either covalent radius or atomic radius. For metals, metals are independent atoms that are adjacent to each other like this. And so we're going to define the atomic radius as this distance right here. Now this is for metals. Now for nonmetals, nonmetals often bind by having their orbitals overlap. And so what ends up happening, we're going to see this in unit 4 and 5 actually, is that if I get the bond or the atomic radius of a bonded atom, it's actually not the actual radius. It ends up being a little bit different. So if I split this in the middle, this would be the covalent radius, which is 1/2 the bond length. whereas in metals, it's actually the radius. Okay, so we sort of use these interchangeably, and it's good to know that when I ask you about the radius for something that is covalently bonded, you're not actually getting the radius, but you're getting something really close to it. And this is just a feature of how do atoms interact with each other. It turns out orbitals can overlap each other in covalent bonding, and we're going to see that in detail in Chapter 5. That's the whole point of Chapter 5. So here are two bromine atoms that are overlapping just slightly. So if I continued the sphere here, and I continued the sphere here, there's this region of overlap. And what that is where the electrons in the bond occur. They both live in that space because you have a nucleus, you have electrons, and a nucleus. And that's how you make a covalent bond. We're going to talk about covalent bonding in Chapter 4. So we'll get to that. But the radius of bromine, we would say, is 114 picometers because the bond between the two atoms, or the distance between their nuclei, is 228. Instead of trying to do a calculation where we try and figure out whatever the hell this is, which is actually very difficult to do. We have to use X-ray diffraction to do that, and it's very hard to do that. But figuring out the distance between the nuclei is a little more trivial. So we just use that and define it that way. Now, how big are atoms in terms of the radius? Turns out that their size varies very wildly. And it totally depends on two features. One is how many energy levels have an electron, so that's N. That's easy enough. Bigger N, bigger atom. Cool, we can do that part. This second part, I'm going to actually write this new variable here called ZEff, or ZEffective. This is a new term that we're going to introduce today. And so this is called the effective nuclear charge. And what this is a phenomenon that can be explained in the following way. All right, here's my lithium atom. This is its nucleus. There are neutrons in here, but we don't give a shit about neutrons because they don't have a charge. In my lithium atom, I have 2 electrons on the outside in the 1s area. So here's 1s. And then I have an electron out here in the 2s area. Now, if I were to describe the force between this electron and the nucleus, or either of those, I would say, oh, what force do I see? I see this. And so does this one. This is what this electron sees, because there's nothing in the way, right? But what does this one see? Well, it sees this, but it also sees this pushing it away. And so this electron on the outside says, well, the force that I'm feeling is 3 pulling me in, but I have 2 electrons pushing me away. So what I think that I'm feeling is that. And this number is called ZEffective, where Z is the atomic number, right? We remember that from writing isotopic notation symbols all day. So ZEffective is just how many protons are pulling me, which is the atomic number, Z, minus how many electrons are shoving me away. And those electrons that shove the outer electrons away are core electrons. Now, S is actually called the screening coefficient. But you can think of S as electrons that shove your target electron. So you're going to have a ZEffective for each energy level. N equals 1, N equals 2, N equals 3, whatever. Only the stuff in N equals 1 will feel all the protons, because there's nothing in the way of them. But stuff further out in like 2s or 2p, 2p and 2s are roughly the same distance, so they don't shield each other very effectively. We're going to look at, for each n, what ZEffective is. And typically, we're going to just be looking at what is ZEffective for valence electrons minus the core electrons, which is why I wrote core here. So this concept is going to come into play for all of our quantum mechanical phenomenon that we're going to study in this section. So today we're going to be dealing with ZEffective a lot. Excuse me. So on this chart here, I have a graph that shows how atomic size is a function of both atomic number and radius. Or I'm sorry, how atomic size is a function of atomic number, because the radius would be the dependent variable there. I'm misspeaking. And as you'll notice, every time I go to a new row, so here are my noble gases. These are the end of a row. When I go to the next period, I go whoop, I jump up in size. And then after that, I rather quickly decrease in size before jumping up again. And then when I get to the transition metals, I kind of slowly change in size, and then I start decreasing again. We're going to explain all of these trends using both quantum mechanical terms that we talked about. So N and ZEffective. That's our goal. We're going to explain atomic size using those two variables. So explaining the jumps every time I add a new ring of electrons, every time I add a new shell number, is pretty straightforward. Those electrons are just further away. But explaining the other stuff is going to be easier if we use this formula here. And this is the secret of chemistry. All objects in the universe that have a charge follow this formula.
But Wes, I thought we weren't doing any more math.
Yeah, we're not doing any more math. So we're only going to care about this formula conceptually. But this formula governs every phenomenon in chemistry. This is it. It's Coulombs Law. Because all entities in chemistry can possess a charge that interact with other matter and cause chemistry to occur, and the most important one of those is the electron, we just follow Coulombs Law to explain universally how all these trends work. Now, let's look at Coulombs Law conceptually and not mathematically. So first of all, if it's mathematically, we don't give a shit about constants. They're just numbers, right? Who cares? This part we do care about, and we can change this equal sign to a proportional. So what are Q? Q is charge. And number 1 and number 2 are the entities that we're looking at. So for example, if I was looking at a proton and an electron and how they were attracted to each other, Q1 would be positive 1 and Q2 would be negative 1 for our purposes. Now, in a physics class, you could get the charge of an electron. You could put positive 1.609 times 10 to the minus 19 coulombs and negative 1.609 times 10 to the minus 19 coulombs. And those numbers we got from Chapter 2. That was when we did Millikan, right? We did the Millikan experiment. We figured out the charge of an electron. We're just going to summarize it as plus and minus 1, because that's good enough for our purposes. It's all a factor of that charge anyway, so we'll just divide that number out. We'll say it's a constant. And then R is just the distance between them. E right here is the potential energy between these two. Now, if I multiply a positive number and a negative number together, the result is a negative number. A negative number represents an attraction. In other words, if I have a potential energy that's negative, I have to put that much energy in to get the system to separate those two entities. But what if I have the same charge? So I put two protons next to each other. Then I get a positive number. Same thing if I put two negatives in here. Then I get a potential energy that is a repulsion. A positive number means that these two things will do this on their own and have this much energy when they push each other apart. So that energy, as a potential, will then get converted to kinetic energy. So if I had 2 protons and I could like hold them in place with my hands, and then I go boop and I let them go, they will sail apart with energy equal to E charge. And that energy starts as potential energy, which is the force they are pushing on each other, and will then become kinetic energy as they accelerate. So that's a little physics background for Coulombs Law. And everything follows this rule, because everything is just point charges, right? Now, obviously, it gets a little messy when you have a system that has like 30 protons pushing on 30 electrons, and everything is pushing each other. But for the most part, we can simplify. And we're going to be looking at pretty simple models anyways. So that's Coulombs Law. That's what we care about here, is that we care about this part right here. What does the sign of the equation tell us? And then we care about magnitude. What do we do to make the number bigger or smaller? Well, if I want to make a stronger attraction, I can do one of two things. I can make this number bigger, or I can squeeze the atoms together. And if I want to make the number smaller in magnitude, I should say, I do the opposite. There you go. I hope the secret of chemistry is in good hands. Please don't abuse it, or you might destroy the world. You will never use this constant. I don't know why I even put it in here, but just in case you were curious what it was, I don't know. All right. Now, if you have taken a physics class, you may have seen this equation with a squared on the bottom. And the reason for that is because if you see the squared term, that's actually force. And energy is force times distance, which would be times this. And those cancel out. So just in case you've taken a physics class and you see that equation again and you're like, wait, I thought Wes had it without the squared on the bottom. Be careful that you're not looking at energy versus force. They're different, but energy is literally just force times distance. Energy being work in this case. I don't know how many people have taken Physics 114. When you get to Physics 242 and stuff like that, this will come up again. So let's get rid of that because that's the equation I want to show. Okay, let's use Coulombs Law to explain all the phenomenon that we've seen so far in atomic size on that chart. So this is my explanation of ZEffective again. We'll go over it a second time. So remember that any charged entity around an atom will feel the following forces. So if you are an electron, you will be attracted to the nucleus. If you are an electron, you will be repelled by other electrons. What we're going to do is we're going to try and use our model. We're going to split everything into n. So I'm going to say this is n equals 1, n equals 2, n equals 3, and then this is the nucleus. So we're going to use a super simple model for this. So let's suppose that I had, let's look at sodium, or no, let's look at magnesium. So magnesium has 12 protons in the nucleus. If I wanted to look at magnesium's electron structure, I would have 1s2, 2s2, 2p6, 3s2. So this would translate to having 2 electrons right here. And they're attracted to the nucleus. And the force that they feel is equal to the full force of the nucleus. In n equals 2, I have 8 electrons, so I'm going to just put all of them here. And those electrons feel the force of the nucleus as well, but they're also being pushed away by the electrons that are closer. So these 2 electrons effectively cancel out 2 protons worth of charge. And so their ZEffective would be 10. And then finally, when we get out here for 3s2, there's effectively 2 electrons out here. They're also attracted to the nucleus, but there's so many other electrons that are in the way, pushing those electrons out, that they screen out the majority of that charge. So the force that these feel over here is only what's left over. 12 minus the 10 that are in the way is 2. So those electrons move around n equals 3 as if they had a force of 2 plus pulling on them. Okay, that's cool. So my ZEffective for electrons on the valence shell of magnesium is +2. Now what I'm going to do is I'm going to hit clear. And we're going to look at another atom in n equals 3. Let's look at aluminum. And we'll go nucleus, n equals 1, n equals 2, and n equals 3. And the reason I'm doing this again is just for practice. Obviously, I could have kept almost everything here, but that's okay. There's my nucleus. That's what's pulling stuff in. And we're going to put our electrons in. So here's my 2 that are being pulled in. Here's my 8 that are being pulled in, but are also repelled a little bit. So they would feel 13 minus these 2 would be 11. And then finally, I have 3 electrons out here, and they're pulled in, but they're also repelled by all the other electrons that are in the way. And I didn't write ZEffective. I probably should have done that. All right. So these electrons out here feel the force of +3. And now here's the kicker. This is where it all comes together. On this blank abyss that I, for some reason, didn't load. There we go. All right. Now we're going to draw a super simple drawing. Here's magnesium. And we got 1, 2, 3s. So these electrons are being pulled in by this force, which we just said, right? Now we'll do the same thing. And these electrons are being pulled in by this force. Okay. Which is going to pull the electrons harder and closer? A force of +2 or a force of +3? What do you think? Think of Coulombs Law, which will increase the potential and thus pull things in closer to it. Bingo, aluminum will, right? Because I have a higher force. What's in the middle here? In this area would be 10 electrons that are pushing out, right? But in this area over here, it's still 10 electrons, so the repulsive force is identical. But as I add electrons on the outside, I'm also adding protons on the inside. And so the effective force that these outer electrons feel starts to increase as we add, or as we go across the periodic table. And so the takeaway that we get here is, as ZEffective increases, atomic radius decreases. There you go. Can't even see it because it's hidden behind my picture. There you go. So you can directly compare any two atoms and figure out which atom will be bigger or smaller. You're going to look at the following qualities. First, look at N. And if something has like N equals 3 versus N equals 2, well, obviously N equals 3 is bigger. There are more layers of electrons. They exist further from the nucleus. But if N is equal, you're going to compare ZEffective. Okay? And that will allow you to compare any two atoms, and that's going to be our whole goal. So now what we can do is we can go back to this slide here, right here. I'm going to clear all of my ink. And we're going to pick pairs of atoms that are next to each other and try and compare their size, why this happens. So I'm going to just pick these two. So that would be literally the two atoms we just looked at. Let's not do that. Oh, wait, no, one was aluminum, one was silicon. You know what, let's go to a different... Let's do these two. So this would be boron. This would be carbon. And I want you to justify to me why boron is larger than carbon. So what I want you to do first is calculate the N for each one. So for boron and then carbon. What is N for each of them? And then I want you to calculate ZEffective. So first draw the diagram for each one. Draw that like rough diagram that I was drawing before, where you separate things into N's. And then count up all the electrons that are pushing away and calculate ZEffective. And then report your answer into the chat, what you got for each of those for their N and each of those for their ZEffective. And then choose the atom that's smaller, although, duh, it's right there on the screen, right? So go ahead and do that exercise. And I'll give you like 3 minutes to sketch out your diagram and then fill in this little impromptu table that I made. And we'll talk about it a little bit more in a second. There you go. Very good. So, using that information that you got, and if people are finishing up, that's fine. Go ahead and take another minute or two to do that. Once you have those numbers, use those numbers to justify why carbon is smaller than boron according to the numbers you got and then the diagram you saw. Do the numbers you got match the diagram? I guess is what I'm saying. We'll go over the answer in one more minute. There you go. That's exactly what I want, is an answer like that. So, now if this was an in-person class, what I would always ask you to do is I would say use quantum mechanics to defend your answer. And so when I say quantum mechanics, that's code for, in terms of N and ZEffective, explain why this is happening. So I don't want you to just tell me the trend. I want you to tell me what is actually happening and what's the we're doing physics. This is physics. What are the physics behind it, not the chemistry? So if I draw my little diagram for the nucleus here, so N equals 1, N equals 2. What these feel is ZEffective plus 3. Because I have... Oops, I should do this. Because I have 5 pulling in and then 2 pushing out. And then same thing for carbon over here, which has 6 in the nucleus. I have 6 pulling in and 2 pushing out. Equals 4 plus. And again, larger ZEffective means smaller radius, so carbon has a higher ZEffective compared to boron. Now, because they have the same N, the one with the higher ZEffective becomes the smaller atom. So we would say that carbon is smaller than boron. Now here's a question. Here are my s electrons. I'm just sort of arbitrarily picking them. And here are my p electrons. S is supposed to be lower in energy than p, so would S push my p electrons away? And the answer is yes, technically, but we're not going to worry about it. So this falls into what's called Slaters Rules, and I mentioned those before, where ZEffective is a much more complex calculation than just how many protons there are minus how many electrons shove your valence electrons away. And you can be using this formula if you'd like. This is pretty straightforward. So here's my Z, and then I have 2 electrons shoving it away. So that would be boron, and that's the number that we got. And then if I want to do that for carbon, here's what's in its nucleus. That many are pushing away. Here's its ZEffective. So if you don't want to draw the diagram anymore, I totally don't blame you. Just use... Oh, shit. Sorry. I'm covering part of my formula there. I totally don't blame you. Use the formula. It's fine. But do these electrons push each other away? The way I rationalize this with a picture is that if these are my s electrons and this is my p electron, they don't push each other away from the nucleus. They push each other away laterally, and there's lots of space. So they repel, and to a first-order approximation, we're going to just say they repel perpendicular to the force of attraction, so they don't exert any force away from the nucleus for our purposes. So other electrons in the valence shell, whether they're s or p or d or whatever, are not going to affect ZEffective. Now keep in mind, that's for the valence shell. So if I have other electrons, and this is going to happen when we get to transition metals, transition metals are weird because those d electrons that I add in aren't valence electrons. They go in n equals 3, right? So n equals 4 will be affected by those extra electrons I'm shoving in there as I increase my atomic number. We're going to do an example of that when we get back from the break, because we're due for a break now. It's already 6 p.m. So let's put this up here. We'll take a 10-minute break. When we come back, we'll talk a little bit more about atomic size and transition metals, and then we'll move on to ionization energy, which is virtually the same topic. So we'll start this, and I'll see you for that in just a bit. Alright, welcome back. I hope you had time to pet a cat. For some reason, Maya doesn't come in here in the evenings to bug us, which is nice, I guess. In my other two classes, all Maya does is she just comes in here every 5 minutes. Meow, it's time to pet me. Meow, meow, meow. It's like, ugh, what can I do to stop my cat from being obnoxious? Alright, so in the first half, we explained ZEffective and how that differentiated two elements like these two on the periodic table. And I could pick any two. They just have to be next to each other in order for ZEffective to be a useful explanation. Because if I picked any other two that weren't next, it's like if I picked boron and then whatever this is, then I have a different end, so I can't really compare them directly. It doesn't work. Now what we're going to do here is we're going to pick two elements that are in the middle that are roughly the same size and try and explain that. So what is this? So this is 1, 2, 3, 4, 5, 6 past potassium. So 2, 3, 4. 1, 2, 3, 4. So this would be chromium and manganese, I think. I don't know why I'm making this so difficult and trying to count which one is which. Let's just pick the first two. Well, let's not pick the first two because it's kind of breaks my example here. Let's pick iron and cobalt, wherever they are. They're in here somewhere. Alright, so to a first order approximation, we're going to look at iron and cobalt. So iron is 26 plus. And cobalt is 27 plus. And so same thing, n equals 1, 2, 3, and 4. And so if I write out the electron configuration for iron, I get this. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, I don't know how many, 6? 6, yeah. And then cobalt would be 7. So let's just fill those in. So I got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d6. So there's all my electrons. So I've got, on the outermost shell right here, I've got 26 pulling in, but I've got all of them but 2 pushing back, right? So these guys push back and these push back. So ZEffective would be Z minus the screening from the core electrons, which would be 26 minus 24 equals plus 2. So that's ZEffective for iron. Now if I go over to cobalt over here, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. And so I'll do the same thing. So ZEffective is Z minus shielding from core electrons. And that's going to be 27 down here, minus, but the extra electron that I added, which is this guy right here, didn't go in the valence shell, it went in n equals 3, right? So this number becomes this. And what do I get? I get the same number, right? So ZEffective for all my transition metals is roughly the same. I just realized you can't see the electron configuration, but that's okay. For all the transition metals, you get basically 2. Now, for the exceptions where you have the half-filled and the totally filled, you end up getting 1. But for a first-order approximation, we get roughly the same ZEffective for all of these atoms. Instead of it increasing each time I go over, for transition metals, it just more or less stays constant. So the conclusion that we get is, if ZEffective is roughly constant for transition metals, then the radius is roughly constant too. And again, this is all for within the same n. And if I go back to the chart, and I look at that, what I see is that, yeah, they are kind of the same for the most part in this region. Like, instead of sharply going down, it even starts to come back up, right? And so on average, they're just sort of around this size. So these are all roughly the same size. And over here, same thing. They're roughly the same size. Now, what is with these little minor deviations in here? That's a little bit more difficult to explain without using Slaters Rules. Just in case you were curious what Slaters Rules are. So ZEffective is always going to be equal to Z. But then this term right here ends up being, so S contributing from lower ends is like a whole electron, but S in an N for an electron that is P is like 0.4, and then S for an electron that's D is like 0.3. It's stuff like this. I don't remember what the exact numbers are, but instead of doing S minus core, you have to actually tabulate all the individual electrons and assign them each a number, and that number isn't necessarily 1. What we're doing here is we're saying, oh, is it not a valence electron? Its shielding value is 1, and so we're just calling everything 1. If you don't do that, then you get different numbers for each of these effectives, and that allows you to predict this result with much better detail. But for our purposes, what we're going to do is we're going to say, oh, look at how constant these all are. It must be because ZEffective is also roughly constant in the middle of the periodic table, and it is. So for our purposes, when you look at the periodic table and you're calculating ZEffective, and you get 2 for your transition metals, you're doing it correctly. They're all 2. Except for anything in column, I want to say it's 6. Yeah, column 6 or 11. Then you get 1, because of the half-filled and the full-filled rule. That's atomic size. We care about n, check n first, and then check ZEffective if both the n's are the same. If both the n's are not the same, you don't even have to worry about ZEffective. Just ignore it. Choose the bigger n, and that's the bigger atom. Alright, I get to skip through all these slides because we've basically just done everything here, so. You can calculate those for practice if you want to. We're going to talk about ionization energy a little bit later. Let's do the comparisons. So, these are our practice problems for atomic size. So I'm going to compare lithium and beryllium. Write out each. Do a little chart like we've been doing here. So N and then ZEffective. Fill in the little chart there. And then choose the smaller atom. And again, you can use the equation for this. So, in fact, you probably should at this point. Oops, hold on. And that shouldn't take you more than a minute to fill out the chart. So, tell me what N is for each of these atoms, and then tell me what ZEffective is. And then choose which atom is smaller based on quantum mechanics that we've discussed. Okay? Type your answer in the chat when you're ready. Double check your N for those. There you go, that's right. Now, which atom is smaller? While you're typing that in, I'll go over the answer here. So, for lithium, they're both N equals 2, because that's the valence shell. And then for ZEffective for lithium, there are 3 protons and 2 electrons in the core, because lithium's electron configuration would be that here are my core electrons, so that's these 2. And then for beryllium, there are 4 protons and has the same 2 shielding electrons. So we would justify this by saying, larger ZEffective for the same N, smaller atom. So beryllium must be smaller than lithium. All right, got to hit clear. Here's the next one, which is bigger. Bigger, be careful. Oxygen or nitrogen? Explain why. So do the same thing. Oops. Just don't mess up there like I did. So for all these problems, you're going to make this little grid here over and over and over again. And just fill it out. And then explain. That's the secret to doing atomic trends, basically, in quantum mechanics. So I'll give you 2 minutes to do that. We'll go over the answer. And we're going to move on to a new topic because I think we've talked about this enough. All right. So for both of these, let me write out the electron configurations. We'll just start there. Oops, that's the wrong end of the pen. So there we go. So the valence shell in both of these is 2, so N is 2. And then ZEffective would be, for oxygen, it'd be 6 protons minus... Oh, it's not 6. What am I doing? It's 8. I can't do math. 6 is the ZEffective. That's why I wrote that. So it's 8 protons minus the core electrons. And then for ZEffective for nitrogen, number of protons minus the core electrons, so it's still 2. All right. And now the question is asking you, which is bigger? Now, I won't just ask you for the smaller one all of the time. Sometimes I might ask you what's bigger. So don't give me all the correct trends and all the way and then pick the wrong one at the end because I asked you for the bigger atom and you picked the smaller one. So if a larger ZEffective means a smaller atom, a smaller ZEffective must mean a larger atom. So nitrogen must be bigger because its ZEffective is smaller. Because if one direction is true, then the opposite must also be true for our trends. Cool. There we go. That's atomic size. Next, we're going to talk about ionic radius. How does the radius change if you add or remove electrons? Well, it changes a lot, it turns out. And we can explain this by looking at ZEffective for cations pretty easily. So let's look at lithium versus lithium plus. We're going to look at the electrons on the outside most layer that is available. So if I look at lithium, here's my lithium nucleus. And at this point, you should know that ZEffective for this electron is 1. So ZEffective for lithium is plus 1. And it has N equals 2, right? Okay. Now let's look at lithium plus. If I make it plus, this all goes away, right? That's no longer there. So let's look at the new situation. And this is now different because it's a different thing. So now I have my electrons. These are the valence shell. So this N is 1. And ZEffective is 3 minus 0 now, right? So ZEffective for these electrons is way higher because there is no shielding coefficient here. So if I ionize something and remove electrons, then both of these things are going to get bigger, right? And so ions get smaller as you remove electrons because the number of protons in the center that is pulling on the electrons is now spread across fewer electrons. And it's going to pull them closer and closer and closer and closer. Now, this will still be true even if I do something like go from magnesium to magnesium plus 1. So for magnesium, I would have 12 plus. So here would be 1s, or here's n equals 1, we'll just say. We'll make it a little simpler. So there'd be 2, and then there'd be 8, and there'd be 2. So ZEffective, so n would be 3 for this, and ZEffective would be 2 for magnesium. If I were to look at magnesium plus, well, n is still 3, and ZEffective is still 2. But by removing this electron here, boop, I now have 12 protons pulling on 11 electrons instead. And you can think of this analogy as kind of like if you are a parent and you are asked to watch over 2 toddlers at the park. You can keep your eye on both of them pretty easily, right? But now let's assume that you are a parent and you are now asked to watch 20 toddlers at the park. That's much harder, right? Because your attention is now spread amongst 20 kids. And you can't see what's behind you or what's going on to the side or why Timmy is climbing up the slide again, even after you told him for the 7th time, no, don't do that. You need adult supervision. Ugh, fucking Timmy. Anyway, the point is that as you have more and more and more electrons, it gets harder to corral them all in, and they get further away. But as you remove electrons, even though you're moving them from the valence shell, the effect is subtle. So what will happen here is that if I had to predict the size for magnesium plus 1, Mg plus 1 would only be a little bit smaller. It might be like 150 or something. But then when I go to magnesium plus 2, and I get rid of this one, everything gets way smaller because now N is only 2 and ZEffective is much higher. I apologize to anyone who's named Timmy out there, especially if you're a toddler. I didn't mean to offend you, but I did check the box that says this lecture video is not made for children. So the effect for electrons within a shell when you're kind of on the way is much, much, much smaller, but it does come into play. So just be mindful of that these trends that we're following aren't perfect for every situation. But for most situations, they will be okay. We will just see giant jumps when we move down to the next N. All right, so that's ions for cations. Let's talk about anions. Now, with anions, size goes up very quickly for sort of the same reason that we just talked about. When we calculate N and ZEffective here, we're going to get the same results each time. So for oxygen, N is 2, and ZEffective is still 6+ for both of these. But there are 2 extra electrons that are present. And it's the attention sort of thing. My nucleus cannot pay attention to that many more electrons. And I'm trying to cram extra electrons into N equals 2, which as you can see is not very big. So to put those extra electrons in, I need to make N equals 2 a lot bigger. And so those extra electrons will get repelled from the other ones, and all of them end up scooting further away. So as you add electrons, your anion gets larger and larger and larger and larger and larger, even before you go on to the next N. So if I had N equals 3, this would actually be a humongous atom. So O3 minus would be humongous. It would be so big that you can't really make it. O3 minus is just too large. That third electron you try and stick on there is so distant from the nucleus, it effectively doesn't see it. And it's just pushed away by other electrons. All right, so the isoelectronic series here is just sort of a summary of what we've talked about. What the isoelectronic series is any cluster of ions or atoms that has the same, the same number of electrons. You can sort their size by number of protons. So for isoelectronic series, I can't spell. Isoelectronic series. What that means is all same number of electrons. More protons equals smaller size. And for cations, you can explain that as, ZEffective is getting bigger and bigger and bigger. And for anions, you can explain that as, ZEffective is smaller. Because if I calculate ZEffective for all of these, for the valence electrons, so N equals, So sulfur would be in n equals 3. This would be ZEffective 6+, 7+. Then I go over here. For potassium, you'd think, oh, it's n equals 4, but I already removed the n equals 4 electron. So this is still n equals 3, but it has a ZEffective of 9+, if you were to draw it out. And we could just do that really quickly. So that's potassium. If I make potassium ion, this last electron goes away. And now I can calculate ZEffective for the valence electrons, which are these, right? So this would be my core. So ZEffective is, potassium's what? 19? 19. And then how many electrons are in the core? It's these 10. And there you go. You could do the same thing for calcium here. So again, a lot of this comes down to ZEffective. Remember that calculating ZEffective for large numbers larger than 8 generally only happens if you have stripped away a valence shell. So you're typically only going to see up to 8. Like if I ask you to calculate ZEffective of argon, it's 8. And then when you add another electron, you've added a new row, and so all of the old valence electrons have become shielding electrons. And so you'd start over with ZEffective as 1. But if you remove that extra valence electron that we just added for the new n level, the previous layer, which becomes the valence shell again, has a higher ZEffective than it did before as a noble gas. All right. I can't find my cursor. There it is. Do I have my summary slide? I do. Okay, so I'm going to just circle the answers here because I really want to talk about ionization energy so I don't get so bogged down. So you can check these on your own. So which one is smaller? So I'm just going to circle the answers. Smaller, smaller, smaller. And then which is smaller? This is smaller, this is smaller. And then this is smaller. I'm going to let you try those on your own just for practice. There's the answers for you, though. And for all of these, remember, you're just using N and ZEffective. All right. Let's talk about ionization energy because I can do that in about, I only have 15 minutes. Well, we'll see. All right. What is ionization energy? Let's draw a diagram. All right. If I want to ionize something, what I'm doing here, here's my nucleus. Let me just quickly draw these in here. Let's suppose that I have... I want to do a new layer, too, here. Let's suppose that I have electrons like, say... we'll do this. And I want to remove an electron. So I'm going to remove any electron. I might as well just pick the last one, right? Ionization is you moving your electron from where it is up to n equals infinity. Because what would end up happening is for whatever atom this is, so this is probably neon, because it has 10 electrons. By doing this process, I would get this. I would create an ion. And the amount of energy that you need to do that, remember this plot's energy. This would be the ionization energy. Now, if I remove one electron, that means that this would be the first ionization. Let's suppose that I have done that. So this electron is now gone. This is why I did another layer, so I could do that. Sorry, I removed that electron. Now let's suppose that I want to do the second one. This would be the second ionization energy. And you might think, oh, they're the same level, right? So first and second are going to be pretty similar. Well, remember that with the nucleus, everything's getting pulled down towards it. And with fewer electrons, it can pull tighter and tighter and tighter, right? So the first ionization energy will be less than the second one, which will be less than the third one, and so on and so forth as you go. Because each electron removed will make my other electrons get closer and closer to the nucleus a little bit each time I remove an electron. In the same way that the radius for my ions in the previous slide decreased when I removed an electron, and then greatly decreased when I removed enough to get rid of the whole layer, right? So ionization energy is just going to be how much energy do you need to pump into your atom to do this? Now, ionization energy is always a positive number. The reason being is that if ionization energy was negative, that would mean that energy would be released when an atom was ionized. And thus all atoms would ionize on their own and all matter would just fall apart. So there's always some attraction to the nucleus by outermost electrons. Now, why are some things very reactive and want to get rid of their electrons? Like sodium, you probably know that sodium wants to do this all the time. It won't do it on its own, but it will do it very easily because its ionization energy is low. So some atoms have low ionization energy, and others have very high ionization energy. The ones that have high ionization energy don't give up their electrons. So we're going to try and predict ionization energy in the same way that we predict atomic radius. And there's a diagram that shows this too. You'll notice that this diagram is kind of like the opposite of radius. In fact, if I could take this diagram and just like flip it horizontally along this axis, or like right here, it would look pretty similar. At least in terms of its trends. So what we're going to notice here is that as ZEffective increases, so if I look at ZEffective here, this would be 1, this would be 2, 3, 4, 5, 6, 7, 8. As ZEffective increases, generally speaking, ionization energy increases too. But then when I go to the next n, so this is n equals 2, and this is n equals 3, it falls right back down. And it falls further and further and further and further down, and you can see that this is slowly going down. So our job is to explain this with ZEffective. And also n. Now n is a lot easier to explain. So let's go to my diagram. We're going to hide this for now. And I'm going to clear everything except for my diagram. And we're just going to draw generic electrons in here. Which electron is easier to ionize? A 3s electron, a 2s electron, or a 1s electron? Well, if I want to ionize 3s, I only have to put this much energy in, right? But if I wanted to ionize a 2s, I'd have to put in this much energy. And then 1s would be even more energy still. So the further away the electrons are from the nucleus, the easier they are to ionize. So as n increases, ionization energy for the first ionization decreases. So what I could do is I could compare two atoms that have different N and the same ZEffective. So if I pick magnesium versus calcium, and I do this, I would see, oh, okay, well, magnesium is N equals 3, ZEffective 2. Calcium is ZEffective 2 also, but N equals 4. Now, when I'm removing an electron, I am fighting the nucleus. The nucleus is always trying to pull my electrons towards it, and I'm just basically playing tug of war. But if the electron is further away, remember Coulombs Law. If this is bigger, the energy of attraction goes down. And thus, that makes this easier for me to pull away. So if I'm only comparing N, the one with the bigger N has the lower ionization energy. It's easier to ionize bigger atoms. We saw this in action when we did, I don't know if you took 140 with me necessarily, but when I showed you the reactions of all the 1A elements in water on the first day of 140, I might have done that in 161, we talked about scientific laws and theories and stuff. We put sodium in water, and it took a little while, and it fizzed about, and it burned in orange, and that was cool. Then we put potassium in water, and it burned right away. And then you put rubidium in there, and it detonates instantly. And then you put cesium in there, and it lasted like 2 frames, like 1/30th of a second. How do you explain that? Well, when those elements are reacting, we're taking their lone S electron away. If I have something from like 6s up here, well, I guess it can't be up there because that's above n equals infinity. This is how much energy it takes to ionize something out of 6s, which would be cesium. That's so little energy that all of the remaining energy that is released by that reaction can be used to show, or to make other atoms get ionized too. And so the result is you get an explosion and a release of energy because there's just so much that's released. As opposed to trying to do this with lithium, where it takes so much energy and you barely get anything out to show for it. So that's ionization energy for N. So if we look back at our little chart here, we can explain that very trivially just by looking at the electron diagram. It takes less energy to ionize things that are further away. That's easy enough. Now, for ZEffective, it's more or less the same picture. Remember that as I remove electrons from things, I'm fighting against ZEffective. So if I'm fighting against a charge of 2+, that's harder to do than if I'm fighting against a charge of 1+. So we'll show that here on our diagram. So I'm going to look at, again, I'm going to look at magnesium because it's just easy. And we'll look at that compared to, say, sodium. So we'll put in my electrons. So there's magnesium. If I want to ionize an electron out of here, I have to fight against the force of the nucleus to do that. So if I want to move my electron that distance from n equals 3 to n equals infinity, I have to put enough energy in to overcome a force of 2+. That would be for magnesium. Okay. Now what we're going to do is we're going to get rid of this. Now I have sodium here. I'm going to remove this electron, but what's fighting against me? Now it's only a force of 1+. I'm moving it more or less the same distance, right? N equals 3 between sodium and magnesium. Magnesium is going to be smaller, so that electron would be further down and closer to the nucleus. So even that's working in our favor too. This electron is both further away and ZEffective is lower. So if I compare their ionization energies, this one should be much harder than sodium. And so we can do this general trend for all of the elements within a period. If I go compare any two together, whichever one has the higher ZEffective within an N, higher ZEffective means that I have a higher ionization energy. Okay, cool. So when I look at my diagram, this should be just a giant slope that goes straight up. And you'll notice, like, there's these really regular things going on here and here. So, and it's always between 2 and 3, right? What's going on here? And then again, between 5 and 6. What the deuce, right? How do I explain these deviations? Like, it should just be a straight slope going like this, if it's just related to ZEffective. So something between 5 and 6 and 2 and 3 must be causing us to suddenly have a lower ionization energy. In other words, it's slightly easier for some reason to pull something away from a ZEffective of 3 than it is to pull from a ZEffective of 2. Let's see if we can try and deduce that. So we're going to hit clear. And we're going to work with, we'll do the first, or period 2. So I'm going to look at beryllium and carbon, or boron, sorry, beryllium and boron. So here's beryllium. And then I'm going to add in another electron for boron. Boop, there it is. Why would it be easier to pull apart from beryllium, or I'm sorry, let me try that again. Why would it be easier to pull boron's electron away against a force of 3 plus than it would be to pull away beryllium's electron when it's only a force of 2 plus? Why is this easier? And the answer to this is, even though my radius is decreasing, remember how we said before that in terms of energy, S is lower in energy than P in terms of potential energy. So this P is higher up in terms of energy than this S is. Remember, that's why we draw them askew like this. It's not quite because it's an incomplete orbital. In fact, we're going to see that the more electrons we put in here, interesting things happen for the 5 versus 6 case. So when you go from 2s electrons to 2p, the ionization energy takes a dip because the next electron is just further away from the nucleus. Now, my diagram is not to scale. It's a little bit exaggerated here. So that difference in distance doesn't look significant, but it's exactly what we're looking for. It's quite a bit, it turns out. So what we care about here is that when we go from S to P, when we, within an N, the ionization energy drops slightly for that transition. And so this is going to be from the 2 plus ZEffective to 3 plus ZEffective. And you can see that that always occurs on the periodic table on our diagram here. Now, after n equals 4, you start getting transition metals in there, and it kind of ruins everything. But that's going to help explain our initial transition right there and why this drop occurs. Now what we got to do is we got to explain 5 and 6. So let's go back to the diagram. And we'll get rid of everything again. And so now what I'm going to look at is I'm going to look at nitrogen versus oxygen. So here would be nitrogen. And then here would be oxygen. So for oxygen, I want to remove this electron. But for nitrogen, I want to remove any other blue electron in the 2p orbital. So it would probably be this one. And when I'm doing this, I'm fighting against 5 plus here. But when I'm doing this with the oxygen one, I'm fighting against 6 plus. And yet, this is still easier to do. It's still easier to remove oxygen's electron. What feature about oxygen makes that easier? What's helping us push that electron out? Because I should be fighting against 6 plus. That's harder. And these electrons for oxygen should even be a little closer to the nucleus. But there is something going on in the diagram that is going to push our electron out a little more easier. It's going to give us a little help. What is that help that's going to happen? I'll give you a hint. There's a reason I wrote it in light blue so you could tell which electron was the extra electron from oxygen in the 2p orbital. And then hint number 2 would be, what do electrons do to each other? We're going to run out of time. So let's just do this. What's going on here? What's special about the orbital that I circled there compared to the other orbitals? You're really close. It's not repulsion from the other upspin electrons, per se. I'll give you another hint. Let's draw the picture of what these orbitals look like. So 2px would be like that. 2py would be in front, something like that. And then 2pz would be in the third dimension like that. And now I'm going to fill in my electrons. So one electron would be in X, Y, and Z. So I'll go 1, 1, 1. And then we'll fill in this light blue electron right here. We'll put him here. What specifically is going to help us push this electron out of the nucleus? Or out of the atom entirely? You're probably typing it, but I'm going to run out of time. It's the other electron that's paired with it. So this other electron, these two electrons are paired in the same orbital. And electrons can pair, but I mean, if they have an opportunity to not be paired, they'll repel each other. So electron-electron repulsion in the same orbital will lower ionization energy. And you can actually see this phenomenon on the graph if we go back to it. So if I go here and I clear all of the stuff that's on the screen here, if there was no electron-electron repulsion after I started pairing them, because up here I only have one electron in each orbital, but then when I get to this next element right here, this is the first time I have to pair them. And that repulsion is going to account for this difference, which you see in all of these. And it just so happens that for the first element after we start pairing, the overall effect is, oh, it's easier to ionize that. So those are our quantum mechanical trends for ionization energy. And ionization energy is really complex. So what we're going to do is we're going to go here in the last minute that I have here. We're going to just summarize. All right, so ionization energy trends. So if I have a higher N, the ionization energy is lower. And the reason for this is electrons are farther from the nucleus. Cool, that one's easy. We can do that one. And then the second one is generally higher ZEffective means higher ionization energy. And that's because we have more pull from nucleus against the electron being removed. That's supposed to be a V, and I can't V today. There we go. And then our exceptions for this right here are, if I go from S to P, P is higher in energy and is easier to ionize. And the first time electrons are paired, the electron-electron repulsion lowers the ionization energy. Okay? So those explanations help us describe the trend in ionization energy that we see on this diagram here. We haven't talked about transition metals yet, but suffice it to say, for transition metals, they all have ZEffective 2, and they all have the same N. Their ionization energy is roughly the same, which is why the slope is way reduced. It's mostly flat. We'll probably pick up there on Wednesday. So Wednesday we'll do the rest of ionization energy. There's not much left. We will do electron affinity, which is the opposite of ionization energy. And then quantum mechanics will be over. And we'll move on to the end of chapter 3, which is like this weird sort of hodgepodge of just like this is what ionic and covalent compounds are, and it'll be back to 140 stuff again before we dig deeper into stuff to get us prepared for Chapter 4. So, we're almost there, believe it or not. But we are out of time for tonight, so I will send you off with a parting of, yeah, quantum mechanics is difficult and it sucks, but keep at it, don't give up. And we're almost at the end of the quarter. There's only like 5 or 6 more lectures left, so we will make it, and we'll get to the end. Have a wonderful rest of your evening, and take care. Have a good one.